Hi everybody. So what I wanted to do in this video is just go over my solutions to the first midterm. Now I already posted some solutions to Canvas, but those solutions I think about as being what I would write down if I were taking the exam. So, I try to fit them into the space on the exam page, and I don't go into a ton of detail there. So I thought it would be a good idea to record a video for you going over my solution in detail, explaining my thought process, and things like that. So let's go ahead and get started on that. Here's the first problem. So this is a problem involving a system of point charges, and we're going to be looking at the electric field and the electric potential from this system of charges. The first part of the problem is, so the setup is we have these three charges which are unknown, right? We don't know the magnitude, we don't know the sign. All that we know is we know the value of the electric field here at this point P. Now, fortunately, we have a lot of symmetry in this problem. All three of the charges have the same value Q, and we have this nice triangular shape here. So that's going to allow us to find the charge from the given information. Let me go ahead and draw this out and label my charges. Okay, again, they're all the same charge, but it helps to label them 1, 2, and 3 so I can refer to them individually. And then I have my electric field here at point P. Okay, and we're told that that electric field points down, and it has this magnitude of 6,700 newtons per coulomb. All right, now the important thing to realize here, the first step to this problem is Q2 and Q3, whatever they are, their fields at point P are going to cancel. And the reason for that is because point P is the same distance from both of them. Okay, they're both, the side length of the triangle is 6 centimeters, so both these charges are 3 centimeters from point P. And since they both have the same magnitude and sign of the charge, their fields are going to have the same magnitude and be pointed in opposite directions. Right? If I were to draw this out, let's just say for example that both of these were positive charges, I would have a field pointing away from Q2 and a field pointing away from Q3 at this point, and they'd be the same magnitude field, so they would cancel. Now, if they were both negative charges, then I would swap these. So E2 would point toward charge 2, and E3 would point toward charge 3, but they'd still be in opposite directions, and they'd still have the same magnitude, so they'd still cancel out. All right, so what that tells me is that the field at point P is entirely due to Q1. Okay, so our field at P is only the field of Q1. Right, that's going to be K Q divided by the distance squared. So the distance here being this vertical distance, which I'll call R1 from Q1 to point P. And we're saying this field, or we're given this field is 6,700 newtons per coulomb. All right, so K is just a constant. I know E. To get Q, I just need to figure out the distance from from Q1 to point P here. And that I can get using the Pythagorean theorem. So I have this triangle. Try to draw an equilateral triangle. Close enough. All right, the side length of this triangle we're given is 6 centimeters, right here. Right, which means point P, which is at the midpoint here, that's this horizontal distance, L over 2, 3 centimeters, from the vertex here. And then this vertical distance, which we're calling R1, we can relate to the other two distances using the Pythagorean theorem. So we have this right triangle here, and if I apply the Pythagorean theorem, I have R1 squared plus L over 2 squared equals L squared. Right? That's just A squared plus B squared equals C squared. And if I rearrange that to get R1, I have this. So take the square root of that. Right, and we could simplify this symbolically, but I'll just go ahead and plug in here. Okay, I have my calculations from earlier because I tried to record this video earlier and messed it up, so we're going again. I have square root of 6 centimeters squared minus 3 centimeters squared. So I get about 5.2 centimeters. Okay. And now I can go back to my electric field calculation and just rearrange this and get Q. So E is KQ over R1 squared, which means Q is R1 squared times E over K. So I'll just plug that in. K, as always, is 9 times 10 to the 9. So I end up with this, about 2 nanocoulombs. All right, that's the magnitude of the charge. Now I need to get the sign. The sign I'm going to get from the direction of the field at point P. And the important thing is that, again, the field at P is only the field due to Q1. So it's pointing down, which in this case means it's away from Q1. And we know that the electric field points away from positive charges. So we know that Q1, and indeed all the other charges, are positive. Right, and so if we're to write down the value of Q, that's just going to be positive 2 nanocoulombs. All right, then moving on to part B. So part B is asking us to calculate the net electric potential at point P. And we're told to take the potential to be 0 at infinity. So this is pretty much just plug and chug. We have a formula for the potential of a point charge. And I know to get the net potential, the total potential, I just add up all of the individual potentials. So I'm just adding up V1, V2, V3. That's going to be KQ over R1 plus KQ divided by L over 2. And the same thing for charge 3. Okay, I can simplify this a little bit for myself. So this is just 2 times all this stuff. All right, and then go ahead and plug in. So there's various simplifications we could make as far as plugging in here. For example, K is 9 times 10 to the 9. Q is 2 times 10 to the minus 9. So the power of 10 actually cancels out here. I could just do 9 times 2, but I'll go ahead and write it out the long way. We have 5.2 centimeters for our distance, and then 2 times all this stuff. And then our distance at 3 centimeters. Okay, and I get this number, so about 1500 volts. So that's our answer. You might be wondering, where did we use the fact that V is equal to 0 at infinity? Well, that just comes in when we use this formula for the field of a point charge, right? So if we say V is kq over r, that's the formula that applies when we have the potential set to 0 far away from all the charges. All right, and then part C, so now we're going to change things up a little bit. We're going to take the bottom right charge, which we labeled Q3, and now we're going to make it negative. We're not going to change anything else. We're going to keep the magnitudes of the charges and the distances the same. But now we have this negative charge, and the problem is asking us to find the net electric field at P, and we want to give that in the form of the magnitude and the angle from the horizontal. So my first step is going to be to calculate the components of the field at point P. So let me go ahead and draw this out. So I have my 2 positive charges, Q1 and Q2, and then negative charge, Q3. I'm looking for the field here. And let me go ahead and pick some coordinates. So I'll just pick X and Y like this. All right, and let me draw out the fields due to all these charges individually. So the field due to Q1 is going to point straight down. Q2 is going to have a field pointing away from it. And Q3 is going to have a field pointing toward it. All right, so now I'm going to calculate the X and Y components of the net field. So I'll have to do that for each of the charges individually and then add them all up. Now, one thing that's really nice here, one thing that simplifies this a lot, is in the vertical direction, our field is only due to Q1. Right, Q2 and Q3, just like in the earlier parts, they're only going to have fields along the horizontal direction. So my Y component is only due to the field of Q1. And nothing about Q1 has changed going from part A to part C, so I'm going to have the same magnitude electric field that I started with. Right, it points down, so the Y component's negative, and the magnitude we were given was 6,700 newtons per coulomb. For the X components, those are only going to be due, I'm only going to have X components for Q2 and Q3. Okay. They're both going to point in the positive X direction, and they're both going to have the same magnitude because they're the same magnitude charge, and they're both the same distance from point P. So I have K, Q, divided by L over 2 squared. And the same thing again for charge 3. Right, and I know everything here, so I can just go ahead and plug in to get the X component. So I end up with 40,000 newtons per coulomb. All right, finally, now that I have the components, I want to find the magnitude and the angle of the field. The magnitude we just get using the Pythagorean theorem. Okay, so that's going to be square root of 6,700 squared plus 40,000 squared. Make this a numerical answer, so I get 41, if we round up to 2 sig figs, I get 41,000 newtons per coulomb. And then the angle, I just get using this inverse tangent formula. Pretty much just plug and chug. So E sub y, E sub y was this one, divided by E sub x. And let me put that in degrees. Okay, I get minus 9.5 degrees. All right, so in other words, my field, if I were to draw it out here, my field is pointing. The negative angle tells me that I'm clockwise from the positive x-axis. So my field's like just below the x-axis here. All right. So that's it. That's everything we needed for the first problem. Moving on now to problem 2. So this problem involves a couple different concepts. We have a parallel plate capacitor, and we're going to need to use the field of the parallel plate capacitor. We have a dipole in that field, so we're going to have to calculate the torque on a dipole in a uniform field. And then part B is a problem we can do using either kinematics or energy conservation for the motion of a charge in a uniform field. All right, so we're told we have this ammonia molecule, and we're given the dipole moment, 3.3 times 10 to the negative 30 coulometers. And we're placing it between the plates of a parallel plate capacitor. The area of the plates, okay, so let me just get this set up. Here are our plates with area 0.7 square centimeters. And we're told to take the positive x-axis pointing to the right. Now the problem says the dipole moment is directed at 25 degrees above the x-axis. In the original version of the exam, I had just 25 degrees from the x-axis, and I believe Jack corrected that for you during the exam. So the intent here was for that to be 25 degrees above the x-axis. And when the dipole is at that angle, we have this magnitude torque, okay? Torque with this magnitude that acts clockwise on our dipole. All right, so let's draw that. So we have the angle here, 25 degrees, and our torque is acting clockwise with this magnitude. 3.2 times 10 to the minus 5, or minus 25 Newton meters. Okay, Now what we're trying to figure out is what is the charge on the capacitor, the magnitude of charge on the capacitor, and which of the plates of the capacitor is positively charged, which one is negatively charged. So let me go ahead and start with figuring out the signs of the charges on the plates. That we can get from the direction of the torque. Remember, the torque is always trying to align the dipole moment with the electric field. And since the torque here is twisting the dipole clockwise, that means that our electric field here is pointing to the right. Okay? Now we're told the electric field is horizontally, so we know it's either going to be pointing to the right or to the left. If it were pointing to the left, then we'd have to twist the dipole around counterclockwise to get it to line up. Right? So the fact that we have this clockwise torque means that our field points to the right. And if our field points to the right, well, then it's pointing from the negative charge to the positive charge. So from our positive charge to our negative charge. Okay, so we've got positive Q over here and negative Q over here. All right, and then we need to get the magnitude of the charge. So that I can work out. Yeah, I know the electric field is Q over epsilon naught A. So if I can find the electric field, then I can get Q. The electric field I get from the torque on the dipole. So this is just this formula, P times E sine theta gives me the torque, and I know everything here except for E. So if I rearrange this to get E, that's just going to be my torque divided by P sine theta, and this I can just plug into. So I have 3.2 times 10 to the minus 25 divided by 3.3 times 10 to the minus 30 times sine of my angle, 25 degrees. I get this electric field, so 2.3 or so times 10 to the 5. All right, then I can go back to this formula and get the charge on my capacitor. So Q is going to be epsilon naught A times E. And this I can just plug in. Now I have to be a little bit careful here because my area is given in square centimeters. So I want to make sure when I'm plugging that in, I plug it in square meters instead. So epsilon naught, that's 8.85 times 10 to the minus 12. My area is 0.7. And then to convert that from square centimeters to square meters, I just take 1 centimeter and square it, so 0.01 squared. Finally, I just multiply by my electric field. Okay, so I get this number, 1.4 times 10 to the minus 10 coulombs. Or we could write that as 0.14 nanocoulombs. All right, so I think, each of the steps here is relatively straightforward. There are just a couple formulas we needed to know, like the electric field on the plates of the capacitor, or the electric field between the plates of the capacitor, the torque on a dipole in an electric field. But we had to put a lot of these steps together. At the end of it, we get this answer. All right, and just let me write down for the sake of being explicit here, our answer, so which plate is positively charged? Well, it's the left plate. All right, then moving on to part B. So now what we're going to do is we have the same setup, same electric field. Now we're going to take an electron and place it in between the plates of the capacitor, exactly halfway between them. We're given the space in between the plates, 1.3 millimeters, and we want to figure out our electron is going to move either left or right. We want to figure out which way it moves, and then what's its speed when it gets to whichever plate it's moving toward. Okay, so here's our capacitor, here's our field. That stays the same as before, same magnitude field as before. And all we're going to do is take an electron and place it in here. All right, now let's figure out which direction the electron is going to move first. This shouldn't be too hard because we know that the electron is going to be repelled by these negative charges here, attracted to the positive charge. So our electron is going to move to the left. And the distance it's going to move is, right, the total distance here was 1.3 millimeters. So the distance the electron moves is just half of that, right? So what is that? That's 0.65 millimeters. Okay, and let me take my x direction to point to the left or to the right. I think the problem says to take the x-axis to point to the right. So I'm going to solve this using energy conservation. Delta K plus delta U is equal to 0. Of course, our potential energy here is electric potential energy. The electron is starting from rest, so we're just going to have 1/2 mv final squared minus 0, because the initial kinetic energy is 0. For our delta U, we can use our formula for the potential energy in a uniform field. That's minus k or minus q e sub x delta x. Now q here, it's an electron, so our q is negative e. Our electric field points to the right, and it has this magnitude that we found earlier, 2.3 times 10 to the 5. So this will be positive 2.3 times 10 to the 5 newtons per coulomb. And delta x, our electron is moving left, which means it's moving in the negative x direction. So this is our delta x. 0.65, negative 0.65 millimeters. All right, so now let me go ahead and plug that in my conservation of energy equation. I'll have 1/2 m v final squared. So it's minus negative e, negative little e, times big E, times negative d over 2. That all adds up to 0. And I have 3 minus signs here. So the second term ends up being overall negative. And now I'm just rearranging to get V final. So that's going to give me E times D for M. And then I can just take a square root. Okay. All right, so let me plug in here. square root of 1.6 times 10 to the minus 19. Our field was 2.3 times 10 to the 5. D is 0.65. D was 1.3 millimeters. Then M, mass of the electron, 9.1 times 10 to the minus 31. So I get 7.3 times 10 to the 6 meters per second as my final speed. Okay. That's the speed the electron has when it collides with the plate, and which direction did it move, which plate did it collide with. Well, it collides with the positive plate, so that's the left one. Okay, so that's it for that. Thank you, everybody. I hope this was helpful. Please let me know if you found it helpful. I'm going to post this to YouTube, so you should be able to leave comments there if you want, or just give me feedback directly. Any suggestions, comments on this video, as I let the motorcycle go by, any feedback on this video would be helpful. I think I'm going to continue to try to post videos. My plan for the next one I want to post is to go over the midterm solutions from last quarter I taught this class, from spring quarter. And then if you have any suggestions for other stuff you'd like me to record videos on, please let me know. And again, anything, if I were to record future videos like this, which I probably will do, going over midterm solutions, any suggestions for those would be really helpful for me. So thank you, everybody, and I'll see you later.